All right, here I want to talk about geometric interpretations of the dot product and the cross product. There are two super important identities involving dot and cross. These are, notice they look almost the same, right? Except just that dot goes with cosine and cross goes with sine, right? So that's something to remember is it's basically the same theorem, works for both dot and cross, right? In each case, it's the product. The left-hand side of the identity is just the product, the vector product, either the dot or the cross, right? And then the right-hand side is the magnitudes of the two vectors you were dotting or crossing, followed by cosine theta or sine theta, followed by the trig function, right? And dot goes with cosine, cross goes with sine, right? So if you can just remember that dot goes with cosine and sine, cross goes with sine, then you can have these two identities packaged up. One thing I haven't said is what's theta, right? Well, theta is the angle between V and W. Right, so that's these are the two important identities to commit to memory. The proofs of these identities are not they're not super easy. This one, at least in two dimensions, you can prove using law of cosines, right? This is it's actually so you could say this is a corollary to the law of cosines. I'm not going to work through that in this video, but it turns out you can derive it from the law of cosines. Once you have that from the law of cosines, then you can use that to prove the second identity by doing a big trig identity bash. Is actually one way you could get it. There are other ways to do it too, but that's probably the most straightforward proof of these. So in this video, I'm not going to focus on those proofs, but rather just on how to interpret these, how to visualize these, what they mean, how to use them, right? How to work with these identities. Because these identities, they give you a lot of intuition, honestly, about the dot product and the cross product and why they're useful, why we like these properties. So let's look at these. In particular, let's start with the first property, right? So this cross or this dot product property. This is great for, if you want to say something like this, find the angle between, let's find the angle between two vectors in 3D. Let's say 1, 0, minus 1, and W, let's say W is 0, 2, 1, right? This is it's clear, very clear what is being asked of us, but this is a horrible question to answer if you don't have this dot product formula. Surprisingly horrible. So this is right here's our three-dimensional coordinate space x, y, z. Now imagine you have these two vectors. So and let's give some color here just to say what we have. So this is let's say v is blue, right? So here's vector v is 1 along the x, none along the y, and minus 1 along the z. So there's vector v is down here, right there, down in the xz plane, right? There's a vector v. Then let's do green for w. And so here's our vector w, 0 in the x, 2 in the y, and 1 in the z. So there's vector w. And then what I want is I want angle theta, right? So angle, we're going to use theta for angle as we do frequently. I want that angle right there, right? So this angle, I mean, just from the picture, you can see, you could guess about what it is, maybe, I don't know, 100 degrees, something like that, right? It looks bigger than 90, just from just a quick sketch, right? But it's not super clear what it is to get a precise calculation of what it is. What's the nicest way to do that? The nicest way to do that is just use this dot product formula. Just plug in. What do you get? You get V. So to do this, I'm gonna apply the dot product formula. I'm gonna apply this formula. I'm gonna say V dot W equals magnitude V, magnitude W, cosine theta, right? And that theta, there's our unknown right there, right? Everything else is known. So I can do this without too much struggle, right? V dot W, now when I say equals magnitude of V times magnitude of W times cosine theta. And now here on the left-hand side, this dot product is just -1, right? These magnitudes, what are these magnitudes? Well, for V, I have square root of 2, and for W, I have square root of 5, right? And so then what do I get? I get that cosine theta is -1 over root 10. There we go. So cosine theta is 1 over root 10. So I get theta is what? See, now I have a formula for it. This theta is going to be arc cosine of -1 over root 10. Right? And if you want, you could even rationalize to get a better formula for it. Arc cosine of negative root 10 over 10. There we go. Now I just got a formula for theta, and it took me, 30 seconds, a minute tops, right? Just carefully working out a dot product and some magnitudes, and we're done. This is something that this would be a hard calculation if you wanted to do this without vectors, right? If you wanted to start, go in here and start drawing triangles and doing trigonometry, oh God, right? It would be terrible. So this is it's a really, really clean tool, right? Because the dot product isn't that bad, right? A little bit of multiplication, a little bit of addition, call it good. So this is our cosine. Now, of course, if you want, you can then get a approximate value for this, right? Once you have the arc cosine, then you can, sometimes it's nice to see what is that then in degrees, right? So let's do that. Let's actually get let's just type it into a calculator, and let's get an estimate for it, right? In degrees, in radians, whatever you like. So let's do that. So here is our, let's pull up, whatever you like, Wolfram Alpha, Desmos, or, whatever your favorite online calculator is, right? So we'll say arc cosine, I'm using Wolfram Alpha, but it doesn't matter too much what you do. So arc cosine of negative square root of 10, right, over 10. And, right, you can type that in, and let's see what we get. Be aware, most of the time you'll get an answer in radians, right, as the default. Just make sure you're aware of that, right? So there we go, arc cosine of this as a radian measure, right? I'm getting 1.89, roughly 1.89 radians, right? And then if you convert that to degrees, that would be 108.4 degrees, right? Which again, from our picture, that kind of makes sense. You can see that it looks a little bit bigger, right? All right, so let's now, a little bit bigger than 90, right? So that's a good example of using this identity for cosine, right? For the dot product for cosine. Finding angles between vectors, great application of this identity. Let's look at another problem that would be really hard to solve without these nice identities. Let's look at, especially with 3D geometry. 2D geometry, sometimes you can just bash your way through it by trig or algebra, but in 3D it gets nasty. So let's look at another problem. Let's say this. How about find the area of triangle ABC given these 3 points. Let's do A is, how about A is 1, 1, 1. Let's say B is 0, minus 1, 2. Let's say C is 1, 0, 2. Right? So let's see what's going on here. What do I have? Let's draw a picture. Always a good place to start, right? X, Y, and Z, right? And then now I have this point A, right? So A is 1, 1, 1. B is 0, -1, 2. So B is like up here. I'm not drawing a super careful picture. I kind of just want something to look at, but you know, if you want to see this better, of course, you can type this into GeoGebra 3D or some computer algebra system, and it's going to look a lot better, right? C is 1, 0, 2. So C is like up here. So there we go. So I have this little triangle, right? And I want to figure out what its area is. That's my goal. Right? I want that area right there. We just shaded it. So that's my goal. Now, this again, if you just start working on trig here, this would be really hard, right? You can get the length of the sides or Pythagorean theorems, but then you need either once you have all three lengths, you could use maybe Heron's formula, or you need an angle to then use to get an altitude or draw an altitude and set up some equations to solve for the length of the altitude. There's no really super clean way to do it. But here with our vector geometry, it ends up being pretty clean. So here's what I want to do. I want to define one vector to be this side AB, right? So that's going to be my vector V. I'm going to call this V. V is going to be the vector that starts at the point A and ends up at the point B. So how can you get those coordinates? So notice here, I don't have V starting at the origin. I have V, A is kind of the origin for V. A is like the tail, and B is the tip, right? So what could I do? I could say, well, it's the difference between point A and point B, right? It's 0, -1, 2, -1, 1, 1, right? If you think of B literally as a vector and A as a vector coming from the origin, then that vector V is the difference. That's how we define vector subtraction, right? It's the vector that would make the tip of one vector meet the tip of the other. So that's a way that you can think of this. Right, what would those coordinates be? It would be -1, -2, and 1. Right? So there's a vector V along that side. Okay. And then let's do another vector over here. Let's say this is vector W. Let's call this W is going to be very similar. It's going to be AC. Right? I'm going to do C minus A. What does this become? This becomes 1, 0, 2, -1, 1, 1. So I get 0, -1, 1. There's vector W. Right. And now here's the key claim. Look at this formula. I claim that an immediate corollary from this is if you just multiply both sides by 1/2, half of the cross product, magnitude of the magnitude of the cross product is the area of the triangle that's bounded by V and W. Why? Well, it doesn't matter if you're in 2D or 3D. The area of a triangle is 1/2 base times height, right? So here, I'm just doing kind of an abstract V and W. It doesn't have to be literally the V and W, the blue and green V and W that we're dealing with in this problem, but this just always works. Because look at this. if you do this triangle, right? Put a side on that, and you want this area, right? What's the base? Well, the base of this triangle is just the magnitude of W, right? What's the height? The height, draw an altitude here, and look at angle theta. The height is what? The height is magnitude V times sine theta. This is just SOHCAHTOA, right? What would sine of theta be? Sine of theta, let's back up a step. Sine of theta is the height over the magnitude of V, right? Because it's opposite over hypotenuse is sine, right? So if you just rearrange that equation, multiply both sides by a magnitude of V, you get that height equals magnitude of V times sine of theta. Okay, so then what is area? Well, area is 1/2 base times height. So what's half of the base? It's magnitude W. 1/2 magnitude W. What's the height? It's mag V sine theta. Oh, there we go. There are, right? This then you could turn into just the cross product. And I would much rather calculate that cross product than find theta or find sine of theta or find both of the magnitudes of V and W separately. It's much easier to do just one cross product than to do all that, especially the theta, right? You can get the theta. You can do what we did here, right? This wasn't too bad. You could use a dot product and get that theta to find the theta between those vectors. You could do what we did up in this example. That's not terrible, but I'd rather not. I'd rather just do a cross product, right? To find theta, that's trig, inverse trig, right? To do a cross product, it's multiplication and subtraction. I'd much rather do arithmetic, right? So that's a lot easier. Arithmetic is easier than trig, right? So this is what we can do now here. We can do what? I can find the area of the triangle that I'm interested in, right? Let's apply this to these, back to our example, right? Let's now calculate, here, we'll switch to red now. We'll now calculate this red area, right? We'll get the area. The area is just gonna be 1/2 of the magnitude, right? Of their cross product, 1/2 magnitude V cross W. So let's do that now. Let's do the area in our example, right? This thing I was saying, notice, this was in general, right? That was sort of an aside. But back to our specific example, what's this area? It's 1/2 V cross W, or the magnitude V cross W. So now let's say what was V and what was W? V was -1, -2, 1. And W is 0, -1, 1. Right. Now let's do this cross product. So what do I have here? I do my X is -2 plus 1. I do the Y is 0 minus -1. And I do the Z is -2 plus 1. Wait, I got the same thing for the X and the Z. This means I have a mistake. Here we go. Yes, I did because it's not symmetric, right? There we go. Yeah, I did the X and the Z. There we go. The Z, or sorry, the X should have been -2 plus 1. Wait, what the heck? Okay, I did the Z wrong. There we go. For Z, what do I want? Oh yeah, there we go. 1 minus 0. That was right. I did it wrong. There we go. So there's my cross product. Let's check that one more time. The X is -2 plus 1. Yep. The Y, see, I was trying to do it without drawing little X's. I should just always draw those. The Y is 0. The Y is 0 plus 1. Yep. And then the Z is 1 minus 0. Yeah, we're good. Okay, cool. So then what do I have? I have here 1/2 magnitude. We now have our vector is going to be -1 plus 1, 1. And this becomes half of square root of 1 squared plus 1 squared plus 1 squared, which is root 3 over 2. There we go. We got the area of the triangle, right? So there's using the cross product formula, right? That geometric interpretation of the cross product. So this is a really nice way to think of the magnitude of a cross product. What does the cross product actually tell you? The cross product is telling you the area of a parallelogram, right? If you doubled this, so the cross product itself is giving you the area of that parallelogram. Then half of the cross product, magnitude of the cross product, gives you the triangle, right? So these formulas, they really that's where cross and dot really enter visual, geometric kind of understanding, right? Is with these two super key theorems. All right, there we go. So there's an example of each of those theorems using it for, say the cosine one, for example, is probably the best way to find the angle between two vectors, right? The sine one is probably the best way to find the area of a triangle or area of a parallelogram, especially in 3D, right? If you're doing 3D geometry. So, great. There is our, so there are two kind of classic vector geometry examples. Thank you.